Okay, section 2 walkthrough on the waves topic, and it was starting to move us into the direction where most of our stuff is, which is about light and different types of light. Last lesson we were talking about the mathematics that went with descriptions of waves, okay, and it was all about these different types of waves. You know, they all related the transverse wave and the particles vibrating around in a sound wave or other longitudinal waves. Now, the question is, electromagnetism doesn't, or electromagnetic light, for example, doesn't need a medium to travel in. It doesn't need particles to go through. Particles actually slow it down by the process it goes through them. So what we need is to move into a slightly different area, and this took a rather long time. It was started with Newton, Isaac Newton again, postulating, because he actually did an awful lot of work on light, much more than he did on forces and mathematics, strangely enough. But he postulated what he thought light was. Interestingly, he used to think it was particles, tiny little particles, and rather like gravity, it kind of accelerated towards things. He was wrong, but there we go. Another guy, a Dutch guy called Christian Huygens, or Huygens if you prefer, he came up with another idea. But either way, it took a good few hundred years more, several hundred years more that is, to actually work out what it was made of. And it was the German Heinrich Hertz who discovered and proved that, and that is why we measure frequency in hertz. So, it's all to do with fields. There's electricity, there's magnetism, and they combine to form a force field, as I'm sure you are well aware from GCSE, that hand prediction gives us all we need to know about electricity and magnetism. And what it means is the current and the field, magnetic field, are always at right angles to each other. So we have this effect going on: electricity and magnetism actually rotating through space, and that disturbance of those electromagnetic fields is what we call electromagnetic radiation. So there is an area that we're going to look into, or a section on electromagnetic light, or electromagnetic radiation more correctly, and that electromagnetic energy, that transfer of energy, is very unique. It's unlike every other wave in that it doesn't need that material. So it's not about the energy of moving things, particles, so on. It didn't need any media to travel, and so it behaves in a completely different way. This is actually energy itself, one format, about the only format that energy itself can exist as its own thing. So, nothing carrying it, therefore it's the energy of the wave itself rather than energy of moving particles. Now, Maxwell, very famous guy, came up with what are continually voted, regularly voted, 4 equations that changed the way the world thought. It's crucial ones that are on our wall in the lab, but they have constantly voted as the most beautiful equations because they bring together beautifully all this stuff. What he did was he studied electric fields, he studied magnetic fields, he studied things that were charged up, he studied how things move. And he basically came up with the idea of electric, and B is magnetic field. He described in a very simple way where it flows from. So electric fields, basically this means that it flows through material from charges from one end to another. And you can look at this as to do a way to find the total. This here, the total magnetism, it doesn't seem to go anywhere because it doesn't actually flow from a charge to a different charge. Magnetism has to go in a cycle, so it's all circular motion. It goes from the North Pole round to the South, for example. So it ends up back where it was, so it adds up to 0. And then what he realised was over distance, over its position, the total position, linked in with other ways as well. And by putting those together, these describing the direction of two fields, and these direct the curve or curl of them, the shape of them, and they link in various other bits and pieces, proved that the shaping of electricity and magnetism can drive energy along. He imagined them rather like clockwork wheels, bit dodgy, but it did work very well. And not only that, but if you put this last equation together and you substitute some of the others in, you'll end up with an equation which gives you how easy it is for electric and magnetic fields to travel. And what you'll find is that when you do that, you find that you get a value of 3 times 10 to the 8 meters per second. So electricity and magnetism can travel as a wave, he presumed, he postulated and proved mathematically, and then it was a while later when people realised, Hertz realised, that he could get this speed by transferring this energy as a wave. And thus, light was born. Hence the joke. So, there are different types of light, electromagnetic radiation. Okay, we know all these from GCSE as well. If you don't know them, there is a particular order. You do need to know the order, and roughly you need to know the size itself. So there is a little acronym. These are not in order, I should say, but gay X-Men use Viagra in my room. Okay, dwell on that for a bit, and I'm sure you'll remember it. But that gives you the order of the spectrum. Okay, gamma rays through to radio waves, X-ray, UV, visible, infrared, microwave, and radio. And all of these are here. Okay, we all can link in, as we'll show in a second, the link, so we can use those wavelengths, the different size of the wave, to work out what the frequency of the source is. And then the idea with this is that these will match across, so there's a few crossing lines, or perhaps use colour if you don't want this to get mucky, and the kind of things that make them. Okay, and you'll find that the smaller the things that make them, basically, the smaller the wavelength they have, which means the higher the frequency. Okay, so try and put them together. The one thing I will point out is that 2 of them are actually in the same area. Okay, so anything less than 1 nanometer, so 1,000th of a millionth of a meter, or a millionth of a millimeter if you prefer, anything smaller than that, hint at the top end of the spectrum, actually both could go into either of these wave bands, either of these types, gamma and X-ray. The difference is where they come from. Okay, gamma, as well you know from radioactivity, comes from an unstable nucleus, alpha, beta particles and gamma rays. Okay, X-rays don't. They come from atoms themselves rather than the nucleus of an atom. Okay, so size-wise, yeah, it's more important. Where they come from is what makes them different. It's not just that they are in order, as was hinted at by GCSE. So these 2 slightly different. Okay, or should we say actually gamma rays are slightly different. Okay, when we do stuff with these, when we've studied them, we find out, because they're basically all about the vibration of charged particles, electrons or atoms or whatever, what you'll find is basically they share the same characteristics, because really they're just same versions of different versions of the same thing. So they all have the same velocity. Or do they? Not quite. They have the same velocity in a vacuum. Okay, so you be careful with that. Be specific enough. So it's not the same velocity, but in a vacuum they're all travelling the same speed. If they were to shine through glass, they would slow down different amounts. Okay, so that idea is really, really important that you've got there. The value is near enough. You know, you can't really get, well, you can obviously, but you can't get a huge amount more detail than that. I seem to remember it's 2.998100. I think there's 3 zeros. So, you know, it's basically that. Now, obviously, if you round those 4 significant figures up to 3, that becomes 0, that one becomes 0, and so it's actually 3.00 in the data book. It's 3 sig fig. To 4, which you'll not need, slightly more precise. Okay? Now, oops, excuse me. The second one is that really, I suppose we could put it together with this, is that you do not need a medium. I know it's higher up, or a media. There we go, plural. You do not need media for it to travel through. But it does help. They are all waves, so they relate in the same way. They all obey, strangely enough, the wave equation, which is of course the one that you all did at GCSE. So C equals F lambda. So with this and that fact, those two facts, we can work out from these the range of frequency for each of them as well. Now these are big numbers, these are like 10 to the 15 to way higher and so on. So this is the one that I would suggest you learn. And most crucially, you learn these ones, which is quite easy to do. You can either think of it in nanometers, 400, 700. It's actually really narrow band compared to the rest. Or if you really wanted to be a little bit harder, 4 times 10 to the minus 7 meters, 7 times 10 to the minus 7. So maybe you like symmetry, 7 times 10 to the minus 7. Doesn't help you with that one. So I tend to go to 400 to 700 nanometers range. Okay, and that one, I think you probably guess already, is quite useful because that's the one that we can see, or rather detect with our own eyes. Okay, all of these, because of the fact they're made in a certain way, all are transverse waves. Okay, the oscillations are at 90 degrees to where they're travelling. And how do we know that? Because of a process called polarisation, which we'll come to in a second. So, and can be polarised. Effectively, that's kind of like flattened. Now, you cannot flatten, I'll say it now, you cannot flatten a longitudinal wave. Okay, you can't put it through a grill and it'll make any difference, because you are basically squeezing it through with your pumping source. But ones that are wiggling up and down can fit through slots or not, depending on the slots. So that's effectively polarisation in brief, but it can only work on polarised waves. So if we use a polarising filter and the wave gets through, we know it's a transverse wave. And then the last bit, there's probably 5 we could do, but we know that all carry energy, but then all waves carry energy. It's not just electromagnetic waves. And we know that a lot of these properties, or some of these properties, like that second one, works for all waves as well, but not all of these together will produce the same properties in all types of waves. And so the last one, all can be reflected, so can a lot of waves. Refracted, less waves can be refracted. And a version that was very important for our next chapter, diffracted. Okay, oh, excuse me. Those two are to do with speed, that one isn't, but it kind of sounds a similar thing, so these always get grouped together. Reflected, refracted and diffracted. Okay, what does that mean? Let's pick up on that to make it work. Okay, some of you may have polarised sunglasses, polarised filters. If you go to the cinema and put your 3D glasses on, they're semi-polarised, which is how they manage to make it work. all kinds of lights that we make on Earth, i.e. humans, that is polarized. And I've put a little video together. I've videoed reflection off water, because if you wear Polaroid sunglasses, it's designed to stop reflections off water. It's designed for sailing, skiing and things like that. So you'll see the difference as I kind of show you what happens here with a simple camera, and more importantly using one set of filters, which happen to be the Polaroid sunglasses. So if I just go back to that picture a second, electromagnetic light spinning through space, wobbling in all directions, or oscillating up and down, left and right, and spinning, so diagonally, and then back to vertical and horizontal and so on. So continuously changing. And I'm going to represent that with this light. Let's just put in natural light. Okay. Vibrating in all ways. And the reason natural light's like this, because atoms in the sun are vibrated in all kind of directions, so they give out radiation in all kind of directions. So what we have with the filter is effectively a tiny series of slits, microscopically. These are on the size of molecules, the separation between them. So there's basically a grain to your filter. Now, if you think of that as a load of bars in a grill, that won't be a bad idea. When I show you the ones in lab, you'll see that these are we use microwave light as well. The microwave radiation, again, it's electromagnetic. We can actually literally put it through a big grill, okay, and it will work. The wave, if it's vibrating in all directions, the ones that line up with the holes will be able to get through. So effectively we've got something called vertically polarized in this version. If you put a second one there, and again the slits are vertical, well, that vertical oscillation still gets through, so it transmits through. If we have a horizontal one, you end up with horizontally polarized. And a second one is still horizontally polarized. However, if we mix them up, so we have our vertical polarization there, but the second one is horizontal, well, because it's wobbling up and down, what we actually do is the energy gets deposited directly into the molecules themselves. It makes the molecules heat up. So the basic idea is it won't get through the slits because the slits are going in the wrong direction. So there is, over here, no radiation. Or no transmitted radiation. Nothing gets through, transmitted through. Now, that might sound a bit odd, apart from looking at the sun, okay, and trying to avoid your eyes being hurt. Cutting out, the idea with Polaroid sunglasses, it just cuts out some of the light, and so less light gets through to your eye. But we can use in lots and lots of other ways, and as we find in the next chapter, when we put waves that kind of cross over, what you'll find is that the waves can cross each other out, okay, unless they're longitudinal, in which case they're not affecting each other in the same way, okay. Someone shouts, someone else shouts, the waves don't bounce off each other and go somewhere else, you can hear both people shouting. But when we make electricity, or use electricity to make waves, for example in radio transmission, TV transmission and so on, what we have is basically a wire, and the electrons race up and down that wire, and that at a certain frequency, and that is the frequency we tune our radio and TV to, and the waves that spread out, if you're going up and down, will be a vertically polarized wave anyway. What we need then is to have, when we pick it up, something that picks up those waves. So in radios we use for mountain rescue, depending how you hold your radio, you can get better signal or less good signal. So if everyone's got their antennas vertical, like that, then everyone gets a good signal. If you try and put it on a rucksack sideways, you get almost no signal, okay, because of this effect. So electrons racing up and down, for example over here, Okay, in our transmitter, again I'll show this in the lesson, as they race up and down, way spread out vertically, if all your aerials pointing at it have the rods vertical, then what will happen is, like the grill, they'll go through, but it will actually make the electrons race up and down. It kind of like our washing, our ripples spreading out, make the ripples go up and down, up and down, up and down. And of course, if we have electrons being pushed up and down, we call that electricity, okay, electric current, and so we pick up the signal. If there's two antennas, two TV masts that are giving out signals, they can interfere with each other. Two radio masts, two telephone microwave transmitters for your telephone. Because they can muck each other up, any that are near each other, some will be transmitting vertically polarized, some horizontal, and the only ones you'll pick up is the ones that your antenna in your phone or radio, TV, whatever, is aligned. So if it's horizontally aligned, you will find you will only pick up the horizontal signals, and they won't affect each other. You'll get a nice clear pattern. We also have some other things, so 4G and 5G is starting to basically just use more levels of polarization, so more different angles, and so your wave, you could actually send, for example, a wave vertical and horizontal carrying different things. You'd actually carry twice as much information in the same time. And so when you go to more angles, you're picking up more information at the same time, fast enough to download and watch live streaming on high quality TV, for example. Okay, so obviously you need to carry more information, therefore you need to get more information in the same time to the receivers. There's another bit we'll show you as well, in that things, when light goes through them, polarizes them as well. So the light shining through a block of material, doesn't have to be visible light, I should point out, distorts depending on the alignment of the molecules in that filter. It's basically acting as a filter. So what you'll find is that if you use a second filter and block out some of the light, you can actually see the stress patterns build up within it. Okay, we can see where the plastic has been poured or the other material has been poured when it was put into the cast. We can see where all the high point stress is, so there's quite a lot of stress there, whereas here there's a little bit. You can see, and this is to basically work on a principle of having a beam, so like a balcony, but they test it by putting weights on it and then shining light through a plastic model, transparent model, and then you can see where the stress patterns build up in the material. So that's a really good way of finding out stress in structures, just by using the idea of light or other types of electromagnetic spectrum, X-rays for example. Okay, so the key idea with this is it's all about imagining stress, and there is a little bit of mathematics about it. If you turn this ever so slightly through an angle, so it's not vertical, it's a bit off vertical, then you get slightly reduced thing. Malus law is linking basically the idea of intensity, how much power you pick up each second, and it links with effectively the sine of the angle. It's trigonometry again. Okay, so it's the same pattern, strangely enough, as the wave itself. Okay, it's a sinusoidal wave, so as you change the angle you get further along, just like our description for a wave. Almost beautiful symmetry there of an idea. Okay, we'll leave it off there. Those are the other parts on light. As I say, I cannot emphasize enough, make sure you know where the boundaries are between the main ones. Make them simple. This one, you know, it's centimetres, it's millimetres, centimetres. This one's much, much smaller, so you can use that idea to put them in order. That one is bigger than 10 centimetres, so if you needed an antenna for it to pick up, to detect your wave, to pick up its energy, you'd need to have something bigger than that wavelength, so 10 centimetres or more. So that's not your mobile phone, because that won't fit in your pocket. So, you know, that gives you some ideas as well. If it's about the size of the nucleus of an atom, Strange enough, maybe it's related to the nuclear gamma rays. Okay, so all that kind of stuff there. Right guys, leave it at that spot, make sure you know those.